Hello all, welcome to this channel cfdbaba. Here we simulate CFD cases using ANSYS Workbench Fluent. Today we are going to simulate airflow over Captain America's shield when he throws it at his enemies. Right-click on Geometry and click on Import Geometry. Select the shield geometry and click on Open. Right-click and edit the geometry in Design Modeler. We will be doing parametric study for different angles of attack of the shield. The shield geometry will be provided to you in the video description down below. You can download the geometry and start your own simulation. Click on Generate. Here you can see that the shield has the grooves on it. There are grooves for handle as well. We will need to select the angle of attack for this shield. Select the shield, click on Create, go in Body Transformation and click on Rotate. Click on Apply. We need to select the axis of rotation. We will select the plane which is normal to our axis of rotation. We will select the XZ plane. We will change the direction by clicking on the arrow. Click on Apply. You can see the angle of the shield is 45 degrees. We will change the angle to 0 degrees for now. We will set parameters for our angle of attack. Click on this white box to set the parameters. Name the parameters as AOA, that is angle of attack. Click on OK. You can see in the workbench that new parameters tab has been generated. Here you can see that the input parameter is AOA, that is angle of attack. Now we need to click on Generate. We now need to create an enclosure around this shield. Go in Tools, select Enclosure. We will select 2 meters in the positive X and the negative X direction. Click on Generate. You can see that the enclosure has been created. Now we need to delete the solid body of the shield from our fluid enclosure. Go in Create, click on Boolean. Select the subtract operation. Select the target bodies as the fluid domain. Click on Apply. Select the tool bodies as the shield. Click on Apply. Click on Generate. You can see that the shield has been removed from our fluid domain and a cavity is left in the fluid domain which is of the shape of our shield. Close the Design Modeler. Open the meshing software. Once the geometry has been imported into the meshing software, we will click on Mesh. Here we will set the element size as 250 mm. Click on Generate. This is just a demonstration simulation. Hence, we will be using a fairly coarse mesh to solve it faster. Switch off and switch on the wireframe mode. You can see in the statistics that the number of elements are 310K. Now we need to select the boundary conditions for our fluid domain. We will assume the flow of air is in positive X direction. Click on this face and press N. Name it as Inlet. Press Enter. Select the outlet face. Press N and name it as Outlet. Now we need to select the shield. You can do that by going in the wireframe mode and change the selection mode type to Box Select. Drag over the shield and you can see that all the faces of the shield have been selected. Press N and type in shield. Press enter. We have all the necessary boundary conditions to solve our problem. Right-click on Mesh, click on Update. This will successfully translate the mesh to Fluent. Close the meshing software. Now, we will open the Fluent Setup. Turn on the double precision. I will use 4 solver processes to solve this problem. Solver processes are the number of pores. Once the mesh has been imported into Fluent, you can see the mesh over the shield. Click on Display. Deselect all surfaces and select the shield. Click on Display. You will be able to visualize the mesh on our shield. You can see that the meshing software has accurately captured all the grooves on our shield. Select all the faces, click on Display. Now we will select the turbulence models. Double-click on Viscous SST Omega. We will be using K Epsilon standard model as it is good for predicting flows in streamline. Next, we will assign the inlet velocity boundary condition. Click on Edit. We will set the velocity of 30 meters per second, that is equal to the velocity of a car on the road. Click on OK. Next, we will select the methods. Turn off the pseudo-transient option. Select second order upwind scheme for all the variables. Next, we will initialize our problem using hybrid initialization. Click on Initialize. Once the initialization has been done, we will select the output parameters as lift force and drag force. Go in Reports and click on Forces. Click on Setup. Here, we will specify the lift force and the drag force for our shield. Select the shield. Select the direction as X. Drag force is always calculated in the direction of our flow. Click on Save Output Parameter. Name the parameter as drag force. Click on OK. Next, we will select the component of direction vector for lift force. Lift force is always normal to the direction of drag force in upward direction. That is the positive Z direction. Select 1 in the positive Z direction. Click on Save Output Parameter. Name it as lift force. Click on OK. Click on Close. Now you will be able to visualize the output parameters in the Parameters tab. You can see that 2 new parameters have been created as the output parameters. So we have one input parameter and we have 2 output parameters. Next, we are ready to solve our case. Double-click on Run Calculation. We will use 100 iterations to run our calculation. Click on Calculate. The Fluent Setup will start calculating the values for our simulation. It shows us the residual graph. Residual graph is nothing but the difference between the actual values and the calculated values. We want this difference to be as less as possible. Residuals of order 10 raised to minus 3 are mostly accepted in many simulations. Let's wait for the calculation to get completed. Once the calculation is done, you will get a calculation complete message. Click on OK. Now we are ready to visualize our results. You can see in the Parameters tab that it has printed the values of drag force and lift force for our AOA 0. Open the Results tab. Here we will visualize the streamlines over our shield. We need to create a location as plane. We will select the ZX plane to create a plane at the midsection of our enclosure. Click on Apply. Hide the plane. Click on the Streamlines button. Select Start From as Plane 1. Select the type as Vertex. Select Number of Points as 1000. Click on Apply. You will be able to visualize the streamlines over our shield. In order to better view it, you can turn on the shield wall. Now you can see the flow of air over and beneath the shield. You can switch on the forward and backward option as well. Click on Apply. Now you can see the streamlines coming in from the inlet as well as streamlines going out through the outlet. Here you can see that the velocity has decreased as the air flows inside the shield curve. We can also view the streamlines in XY plane. We will create a new location. Select the method as XY plane. Click on Apply. This will create a plane just above the shield. Select -0.03. Click on Apply. This will move the plane to the midsection of our shield. We will plot streamlines on this plane. Switch off plane 2. Double-click on streamline 1. Select Start From as plane 2. Click on Apply. Now you are able to visualize the flow of air over and below the shield more accurately. You can see that the air speeds up as it goes from above the shield, and there is recirculation zone formed below the shield inside the shield curvature. This is how you can post-process your results inside CFD Post. Change the maximum points to 10. Click on Apply. Switch off the streamline. Now we will conduct a parametric study for different angles of shield. Close the CFD Post. Close the Fluent tab as well. To set the parameters, go in the Parameters tab. Here we can see the current design point as AOA 0, and these are the output values of drag force and lift force. Select design point 0, right click and select duplicate design point. Do it again for design point 1. We will use -10 degrees and +10 degrees as our input parameters. -10 degrees will rotate the shield in the downward direction, and +10 degrees will rotate the shield in the upward direction. We will calculate the values of lift and drag forces for these two angles. To calculate these values without having to do the simulation over again, we can use this parametric study by the help of changing input parameters in design points. Select both the design points, right-click, and click Update Selected Design Points. You can see your progress by clicking on the Progress button. You can see that currently the software is updating the geometry and mesh component for design point 1. This automatically solves our simulation for different input parameter conditions. This helps us to save a lot of time by saving our time in the solution setup by doing the geometry and meshing and boundary condition setup again. This will take a while to update both the design points. Let's wait. Once the design points have been updated, you can see the values of lift force and drag force for both the angles of attack. If the shield is going in negative angle of attack, you can see that the lift force has become negative. Whereas if the shield has positive angle of attack, then the lift force has increased with respect to 0 AOA. Also, the drag force has increased. This hardly took 10 minutes to solve, which is a lot quicker than manually setting up the whole case again for these two angles. First, save your project in some local folder. Then select these two design points, right-click and select Export Selected Design Points. This will create two new projects. Click on Open Project. You can see that Design Point 1 and Design Point 2 have been created. We can view the results from Design Point 1. Open the Design Point 1. Save the current project. This will open up the Design Point 1 simulation. Here we had the negative angle of attack. Let's visualize the results. Open CFD post. You can see that the shield has been rotated in the downward direction. This angle is minus 10 degrees. Let's visualize the streamline flows again. Double-click on Streamline. Set the number of points to 100. Click on Apply. You can visualize the change in streamline patterns when Captain America is throwing his shield in a downward direction to hit his enemies. You can see that more vortex generation is getting formed below the shield curvature. Set the points to 10. This will minimize the load on your CFD post. Let's visualize the results for AOA 10 degrees. Open Design Point 2 project. Save the current project. Go in the Results tab for Design Point 2. Here you can see that the shield has been rotated in the upward direction. This will simulate the case when Captain America hits aliens in the skies. Switch on the Streamline 1. Select the number of points as 100. Click on Apply. You can see that there is less vortex generation formation below the shield surface now. That's why we are getting higher value of lift and drag when the shield is traveling in the upward direction. This is how we can do parametric study of different objects inside ANSYS Fluent Workbench. If you have liked this video, be sure to click the like button and also click the subscribe button. Share it with as many friends as possible. We will meet again in a new video with a new simulation. Goodbye till then.